So this is the area between two curves, dy addition. Think about it like CSI when they went to all those different cities. Not that I have any idea where they went, but so now that I'm a prolific video artist, I'm going to do a little spin-off series for dy. The basic idea is the following. I know I alluded to this in the previous video, but if you have some curve like that and that, you can see that, well, maybe you can't see. Let's see in a second. So I'm trying to make the same picture twice there. Option number one is, oh, well, I'll just keep doing what I've been doing, which is to make little slices like this. The problem is in this area right here, that the slice goes from this function and out the back side of it. And that's no good, because we've got to worry about signage there. I mean, you can do it, but you have to break it into two pieces, because let's do it this way. In the green region, it's actually the line minus the parabola. The line is on top of the parabola. In the red region, and again, both of these, green and red, are both in the enclosed region. In the red region, it's the parabola minus itself. So, plan B, which is better plan, is to go this way. That way, you always have a defined, which function is further out. Now, the way we're going to determine this length, because this length is going to be now the height of our rectangle, right? Over here, the heights of the rectangles were based on y values minus y values, right? So some y value minus another y value, y sub 1 minus y sub 2. And then we integrated and we multiplied it by the width of each rectangle, which we call delta x or dx. Over here, we're going to take some x value minus another x value, and then the width of the base of each of these rectangles is going to be some small increment in y. So instead of slicing this way, we're now going to slice horizontally. And you can see hopefully why it makes a lot more sense in this problem to do just that. So we're just going to do one of these, and it's going to be the following. We're going to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So we want to find, this is just our example, find the area of the enclosure. You can see, obviously that's going to make a line and that's going to make a parabola, but the parabola is going to face side, and it's going to be side to side instead of up down. So the first thing we need to do is find when they meet. And the easiest thing for me to do with that, I guess, would be to isolate x. So in that equation, it's y plus 1. And in this equation, it's y squared minus 6 over 2. And then we can solve that quadratic. The points of intersection are -1, -2, and 5, 4. So now to get an idea of the picture, -1, -2. And 5, 4. And so our picture kind of looks like that. I fully realize there's probably all kinds of detail that is not very good in there, but that's okay. Now, what we need to do is think about this as before, if we were to try to approach this as dx problem, we would use the higher y value minus the higher y value minus the lower y value. So in this case, think about it integrating the rightmost x value minus the leftmost x value, because the rightmost x values will be larger with respect to y. So in this function, it's going to be y plus 1, right, because the line is on the right side, minus y squared minus 6 over 2. Because the parabola is on the left side, dy. And now it's important to think about those limits of integration. So give yourself a second and try to figure out, we've obviously got the points, but what values do we put in here and here? So give yourself a second to think about that. Hopefully you have thought about that now. Remember that we're slicing in this direction now. So we want to go, our lowest y value, we're going to look this way, and this tells you to look at the y values. The lowest y value is -2 and the highest is positive 4. So think about it as dy, meaning slices in the y direction. Starting from down here, the width of each rectangle is determined by that right x value minus left x value. And the base of each rectangle is dy, and we're going to slice all the way up until we hit positive 4. And I'll leave you to finish that, but you should get 18. So this would be 18 square units. So hopefully this has given you a little bit of a flavor of exactly, A, when is it useful to use dy integration, and B, how do you execute? Just to recap, when is it useful? Well, it's useful here because I don't have to deal with isolating y. I can isolate x pretty easily and then go from there. And secondly, it alleviates the concerns about having to subtract a function from itself in a certain region if we were to try to cut it this way. So basically, you'll be able to recognize it algebraically when you see, oh, I don't want to, if I take the root of this, I don't want to have to integrate that thing. But if I isolate x, I can easily integrate the rest of it. So hopefully that was productive, and we will continue with this idea when we study volumes of solids of revolution between integrating either dx or dy.